In the last video, I touched on the idea of a sigma bond. And that was a bond where, let me draw two nucleuses. And let me just draw one of the orbitals. Let's say that this is an sp3 hybridized orbital. And that's on this atom. And this is kind of its big lobe right there. And then this guy has an sp3 hybridized orbital as well. That's the small lobe. And then that's the big lobe like that. A sigma bond is one where there's an overlap kind of in the direction in which the lobes are pointed. And you might say, well, how can there be any other type of bond than that? Well, the other type of bond, so this right here, let me make this clear. This right here is a sigma bond. You're saying, well, what other kind of bond could there be where my two orbitals overlap kind of in the direction that they're pointing? And the other type of bond you could have, you can imagine if you have two p orbitals. So let me draw the nucleus of two atoms, and I'll just draw one of each of their p orbitals. So let's say that that's the nucleus, and I'll just draw their p orbital. So p orbital is just that dumbbell shape. Let me draw it a little bit. Let me draw them a little bit closer together. So p orbital is that dumbbell shape. So let me draw this guy's one of his p orbitals. I want to draw it a little bit bigger than that. You'll see why in a second. So one of his p orbitals right there. It comes out like that. And then this guy over here also has a p orbital that is parallel to this p orbital. So it goes like that. So it goes like that. Well, let me draw that other one a little bit straighter. It goes, I want it to overlap more. So it goes like that. I think you get the idea. So here, our two p orbitals are parallel to each other. You can imagine these are sp3 hybridized orbitals. They're pointing at each other. Here, they're parallel. P orbitals parallel to each other. And you see that they overlap on this kind of top lobe here and in this bottom lobe here. And this is a pi bond. So let me make this clear. That is and this is one pi bond. So you could call it a pi, literally with the Greek letter pi bond. Sometimes you'll see this as just written as pi bond. And it's called a pi bond because it's the Greek letter for essentially p. And we're dealing with p orbitals overlapping. Now, sigma bonds, which are what form when you have a single bond, these are stronger than pi bonds. Pi bonds come into play once you start forming double or triple bonds on top of a sigma bond. And to kind of get a better visualization of how that might work, let's think about ethene. Ethene. So its molecular structure looks like this. So you have C double bonded to C, and then you have each of those guys have two hydrogens. Each of those guys have two hydrogens. So let me draw what it would look like, or our best visual, or our best ability to kind of conceptualize what the orbitals around the carbon might look like. So let me draw. So first I'll draw the sp2 hybridized orbitals. So let me just make it very clear what's going on here. So when we were dealing with methane, so methane, which is literally just a carbon bonded to four hydrogens. And if I actually wanted to draw it in a way that it kind of looks a little three-dimensional with a tetrahedral structure, it might look like this. This hydrogen is pointing out a little bit. This hydrogen is kind of in the plane of the page, and then maybe that hydrogen is behind it, and then you have one hydrogen popping up. That's methane. And we saw that these were all sp3 hybridized orbitals around the carbon, and then they each formed sigma bonds with each of the hydrogens. We saw that in the last video. And when we drew its electron configuration, in order for this to happen, carbon's electron configuration when bonding in methane needed to look like this. It needed to look like 1s2, and then you have, and then instead of having 2s2 and then 2p2, what you essentially have is, let me write it this way, actually, even better. Let me write it this better. In 1s, you had 2 electrons. And then instead of 2s, you had 2 electrons, and in each of the p's you had 1. The s's and the p's all got mixed up. The s's and the p's all got mixed up. And you had a 2 sp3 hybridized orbital, another 2 sp3 hybridized orbital, another 2 sp3 hybridized orbital, and then another one. sp3. Normally, when carbon's sitting by itself, you would expect a 2s here, and then you'd have a 2p in the x direction, a 2p in the y direction, and then a 2p in the z direction. But we saw in the last video, they all get mixed up, and they all have a 25% s character and a 75% p character when carbon bonds in methane. And then the electrons kind of separate out in that situation. When you're dealing with the carbons in ethene, remember eth is for two carbons, and ene because we're dealing with an alkene. We have a double bond here. In this situation, the carbon's electron configuration when they bond in ethene looks more like this. So you have your 1s, and then you have and the 1s orbital is still completely full. It has two electrons in it. But then in your 2 shell, you have, so let me do this in a different color. So in our 2 shell, I'll show you what I mean in a second. I'm not writing the s or p's so far on purpose, but we're going to have 4 electrons just like we had before. We're still forming 4 bonds. We're going to have kind of these 4 unpaired electrons. We're still forming 1, 2, 3, 4 bonds with each of the carbon. So they're going to be separated out. They are going to be separated out. But in this situation, instead of all of them being a mixture, kind of 1 part s, 3 parts p, the s mixes with 2 of the p orbitals. So what you have is 2sp2, 2sp2, 2sp2 orbitals. So you can imagine that the s orbital mixes with 2 of the p orbitals. So now it's 1 part s, 2 parts p. And then one of the p orbitals kind of stays by itself. And we need this p orbital to stay by itself because it is going to be what's responsible for the pi bond. And we're going to see that the pi bond does something very interesting to the molecule. It kind of makes it unrotatable around a bond axis. And you'll see what I mean in a second. So let me see if I can, in 3 dimensions, draw each of these carbons. These carbons. So you have, let me do it in a different color. You have this carbon right there. So let's say that's the nucleus, although I'll put a C there so you know which carbon we're dealing with. And then I'll draw, you could assume that the 1s orbital, it's really small right around the carbon. And then you have these hybridized orbitals, the 2 sp2 orbitals. And they're all going to be planar, kind of forming a triangle, or I guess maybe a peace sign on some level. But I'll try to draw it in 3 dimensions here. So you have one, this is kind of coming out a little bit. Then you have one that's going in a little bit. And then you have, and they have another, lobe a little bit on the other side, but I'm not going to draw them. It'll complicate it. They still have characteristics of P, so they'll have 2 lobes, but one is bigger than the other. And then you have one that's maybe going in this side. So you can imagine that this is kind of a Mercedes sign on, if you drew a circle around it, on its side. So that's this carbon right here. And of course, it has its hydrogens. So you have this hydrogen there. And so this hydrogen might be sitting right here. It just has 1 electron in its 1s orbital. You have this hydrogen up here. It's sitting right over there. And now let's draw this carbon. Now let's draw this carbon. This carbon will be sitting, I'm drawing them pretty close together. This carbon will be sitting right there. He has his 1s orbital. They have the exact same electron configuration. He has his 1s orbital right around him. And then he has the exact same configuration. And either of these guys, we've so far only, or in this first guy, I've only drawn these first 3. I haven't drawn this unhybridized p orbital yet. So I'll do that in a second. But let me draw his bonds. So first of all, he has this, or you could imagine that bond right there, which would be an sp2 hybridized bond. Let me do that in the same color as. So he has this bond right here, which would be an sp2 hybridized bond. Just like that. And notice this is a sigma bond. They overlap in kind of the direction that they're pointing in. That's the best way I could think about it. And then he's got these 2 hydrogens. So one, he's got this guy in the back, this guy in the back, and then there's one in the front. I'll draw it a little bigger so it's kind of pointing out at us, right? And then we have this hydrogen is sitting right over here. And these are also sigma bonds, just to be very clear about things. This is a s orbital overlapping with an sp2 orbital, but they're kind of overlapping in the direction that they're pointed, or kind of along the direction of each other, of the 2 atoms. This is a sigma bond, and then we have this hydrogen in the back. We have this hydrogen in the back, which is also going to form a sigma bond. So everything I've drawn so far is a sigma bond. So that, maybe I don't want to make this picture too. So I could just put sigma bond there, sigma bond there, sigma bond there, sigma, sigma. So far I have drawn this bond, this bond, this bond, this bond, and this bond. All of those sigma bonds. So what happens to this last p orbital for each of these guys? Well, that's going to be kind of sticking out of the plane of the Mercedes sign is the best way I can describe it. And let me see if I can do that in a color that I haven't done yet. Well, let me this little purple color. So you can imagine a pure p orbital. So a pure p orbital, and I'll draw it. I need to draw it even bigger than that, actually. A pure p orbital. It normally wouldn't be that big relative to things, but I have to make them overlap. So it's a pure p orbital. A pure p orbital that's kind of going in, maybe you can imagine the z-axis, that the other orbitals are kind of a Mercedes sign in the xy plane, and now you have the z-axis going straight up and down. Oh, and those bottom two have to overlap, so let me draw them bigger. So it looks like that, and it looks like that. And they're going straight up and down. And notice, they are now overlapping. So this bond right here is this bond. I could have drawn them in either way, but it's that second bond. And so what's happening now to the structure? So let me make it very clear. This right here, that is a pi bond. And this right here is also, it's the same pi bond. It's this guy right here. It's the second bond in the double bond. But what's happening here? Well, first of all, by itself, it would be a weaker bond. But because we already have a sigma bond, since we already have a sigma bond that's kind of that's making these molecules come closer together, this pi bond will make them come even closer together. So this distance right here is closer than if we were to just have a single sigma bond there. Now, on top of that, the really interesting thing is if we just had a sigma bond here, both of these molecules could kind of rotate around the bond axis. They would be able to rotate around. They would be able to rotate around the bond axis if you just had one sigma bond there. But since we have these pi bonds that are parallel to each other and they're kind of overlapping and they're kind of locked into that configuration, you can no longer rotate. If one of these molecules rotates, the other one's going to rotate with it because these two guys are locked together. So what this pi bond does in this situation is it makes this carbon-carbon double bond, or it means that the double bonds are going to be rigid. That you can't have one molecule kind of flipping, swapping these two hydrogens without the other one having to flip with it. So you wouldn't be able to kind of swap configurations of the hydrogens relative to the other side. That's what it causes. So hopefully that gives you a good understanding of the difference between sigma and pi bond. And if you're curious, when you're dealing with just to kind of make it clear, if we were dealing with ethine, so that this is the example of ethene, but ethine looks like this. You have a triple bond, and so you have each side bonding to one hydrogen. In this case, one of these, so the first bonds you can imagine, so these bonds are all sigma bonds. They're actually sp hybridized. Your 2s orbital only mixes with one of the p's. So these are sp hybrid orbitals forming sigma bonds. So all of these right here. And then let me do this in a different color. Both of these are pi bonds. And if you had to imagine it, you could imagine another pi bond kind of coming out of the page, and another one here coming out of the page and into the page, out and into the page. And they too are overlapped, and you just have one hydrogen pointing out in each direction. Maybe I'll make another video on that. So hopefully